The topic this morning is control functions and related methods, and I'll try to use my full allotment of time this time. I think with control function methods, like with much of econometrics, part of it is just figuring out what the terminology is. And I think what people mean by a control function method has evolved a little bit, but I think it's more or less settling down, and I'll try to start with things that are probably familiar and then connect it to the more recent literature. One thing to remember is that, as I say in topic 3 here, about limitations of the control function approach, is there's actually still a very broad class of models where we don't have any good, robust approaches to estimation with endogenous explanatory variables. So this is we're thinking of these as instrumental variables methods, and they're usually applied in nonlinear models, although you know of some cases where they're applied in linear models as well, so I'll briefly review that. So if we start with a linear model, of course, most of the time we estimate this in the simplest cross-sectional case with random sampling. We usually use something fairly simple like two-stage least squares, or if we want to try to get a more efficient estimator and there's heteroscedasticity of unknown form, we can use generalized method of moments. But the point is, we know that there's a set of estimation methods that may or may not work well, but that has to do with the quality of instruments and identifying assumptions. The alternative approach that I'll quickly derive, or at least show you what the estimating equations are, it would be surprising if they didn't rely on the same sort of identification schemes. The identification gets a little different when we look at nonlinear models, but in terms of the linear model, how one goes about identifying using a control function approach is the same as using standard instrumental variables approaches. So let's just start with equation 1, where the response variable is y1, and we have exogenous covariates z1, and then for simplicity, I'm just considering the scalar case here, where y2 is a scalar, and then u1 is the error. And then, of course, we need an exclusion restriction. We need an instrument for y2, and so this vector z has at least one more element than z1 does. Now, one thing to remember is if we estimate this equation by two-stage least squares, say, then the key condition, I didn't put the rank condition down on the slide. The key exogeneity condition is given by 2. And if we estimate this equation by two-stage least squares, one thing to keep in mind is that it doesn't restrict the nature of y2 at all. Okay, y2 could be a binary variable. It could be continuous. It could have Tobit-like characteristics. The two-stage least squares in GMM don't care about the nature of y2, because in the first stage, all that's being imposed is this reduced form, which is a linear projection. So equation 3 is definitional. Okay, I'm not worried about whether variances exist and so on. In any practical case, we just assume that they do. And so 3 is a definitional equation, and so it holds no matter what the nature of y2 is. Okay, of course, if we start making assumptions on v2, such as it's independent of z, or even just that it has a zero conditional mean, then we start making substantive restrictions on the reduced form. Okay, but the way that linear IV methods work is precisely not to make that sort of assumption. Okay, that it's just definitional. Okay, but the point of this is to try to connect that to control function methods in this simple case. So everything so far is basically, you can think equation 2, of course, is an exogeneity requirement, but it's stated in terms of zero correlations. That's actually going to play a role later on. We have to, in nonlinear models, state exogeneity in stronger terms than that, but for now we just state it like that. And the control function method then proceeds by writing the structural error, if you will, U1, as a linear function of the reduced form error, and then there's something left over. Again, equation 4 is definitional. Okay, so it doesn't matter that V2 might have some discrete characteristics, for example. It's just a linear projection where rho 1 is given there as the population regression coefficient. Okay, so if you, again, whenever we write down a linear projection, by definition, the error in that linear projection is always uncorrelated with the thing we projected on, and so E1 and V2 are uncorrelated. Well, E1 is a linear combination of U1 and V2, so E1 is also uncorrelated with all of the exogenous variables Z, which means that E1 is also uncorrelated with Y2 because Y2 is just a linear function of Z and V2. Okay, that's a lot of words to say something that's fairly obvious, but the point is, if we then essentially we take the structural error and we replace it with this projection onto the reduced form error, and we wind up with equation 5. So in this equation, what have we accomplished? Well, think of V2 now as a regressor. We can't observe it, of course, but we're going to estimate it. But when we talk about identification schemes, of course, any parameter that can be consistently estimated, we just treat as fixed. So in equation 5, we have this new regressor V2, and now we have the error term as E1. But as we just went through, E1 is now uncorrelated with everything on the right-hand side, including Y2. Okay. Now, of course, if you look at that equation, V2, it's a linear function of Y2 and all of the Z's. If we didn't have extra Z's in equation 3, then V2 would be an exact linear combination of Z1 and Y2, and then that equation would be useless to us. Okay, so the fact that we can put V2 in as a regressor there means that we have to have something extra in Z that shows up actually in 3. This is exactly the identification condition for two-stage least squares. Okay. So the control function approach says instead of essentially instrumenting for Y2, some people like to think of it as taking the fitted values from the first stage regression and plugging it in for Y2. That's certainly algebraically the same. We leave Y2 in the equation and we add V2 as a regressor, and that controls for the endogeneity of Y2, hence the name control function. Okay. Now, to implement this, of course, we need to do a two-step procedure, and the first step is to estimate the reduced form, just like you do with two-stage least squares, at least in the background, if you are thinking of it that way. And then in the second step, you just add the V2 hats as a regressor. And of course, standard results on two-step estimation tell you that this is going to be consistent. Standard results on two-step estimation also tell you that the standard errors that you get from this regression are not going to be valid in general because of this generated regressors problem. Okay, so V2 hat, the way to think about it, of course, is what we've done is we've replaced pi 2 with pi 2 hat, which depends on the same sample. And so there's sampling error in this regression due to the first stage estimation of pi 2 hat. And so you could ask, why would you do this regression instead of just using two-stage least squares? And the answer is you wouldn't. but the point is that when we get to other applications, this is quite convenient, and they're really the analogs of two-stage least squares are less preferable. Okay, so there are two reasons why there's one good reason for doing this regression, so I shouldn't say you wouldn't. The good reason is because this gives you a simple way to test whether Y2 is exogenous. In fact, this is equivalent to the Hausman test that compares the OLS estimate and the two-stage least squares estimate, is to just do a t-test on V2 hat. That's valid because if you notice what happens when rho 1 is equal to 0, the estimation error from pi 2 hat is no longer there. So the t statistic, and typically you want to make this robust to heteroscedasticity. But I should emphasize, you don't make it robust to heteroscedasticity because of pi 2 hat. Okay, that does not correct for the first stage estimation. You make it robust to heteroscedasticity because the structural error might have heteroscedasticity. Okay, so generally the adjustment you need to make if rho 1 is different from 0 is not so straightforward as just making it robust to heteroscedasticity. Some time ago there was confusion on that point. I don't think there's much anymore, but just to emphasize that. Okay, so one reason to do it is a simple test for the null hypothesis that y2 is exogenous. The reason not to do it is the standard errors. You can't just use the standard errors from this regression if rho 1 is different from 0. And probably the even better reason is that this turns out to be identical to two-stage least squares. So you get this extra estimate rho 1 hat, which, like I said, can be used to gauge whether y2 seems to be exogenous or endogenous. But the coefficients delta 1 and alpha 1 hat, those are the same as doing two-stage least squares. Okay. So probably that's why you don't see this discussed very much in the standard linear case, because it reduces to something that we already know about. Okay. So as I said, these are control function estimates, and they really don't give us anything new. What the approach does give us is a way to test for exogeneity. Hausmann noticed this in his paper back in 1978 on specification testing. So things actually get different once we change the model just a little bit. So this is 7 is still a linear model, but it's linear in the parameters, but now a nonlinear function of the endogenous variable has been inserted or added. So this is not a crazy model, right? We might want an endogenous variable to have a nonlinear effect. And the nature of the exogeneity assumption now is given in 8, and this is actually critical for these kinds of models, that it doesn't well, I should be a little careful. Usually you need to make an assumption like a conditional mean assumption to be able to identify the coefficients. There are exceptions to that, but to be able to use a broad class of instrumental variables estimators for these kinds of models, you should replace the zero correlation assumption by a zero conditional mean assumption as an 8. Okay, so let's just take a simple case where we have one omitted variable z2 that we've assumed is exogenous and is in the reduced form for y2. Okay, whatever. So let's just say in the linear projection of y2 on all the z's, z2 appears there. Then what can we do to estimate the parameters of that equation? Well, we need instruments for y2 and y2 squared. And while this would be inefficient, a valid instrument for y2 squared is z2 squared, ruling out the case where z2 is a dummy variable and then its square would be itself. So we would have to do something else in that case. So we could just estimate that equation by standard, I'll just say standard instrumental variables, because what one means by two-stage least squares might be wrong in this case. But in any case, we just list the instrumental variables as z1, z2, and z2 squared. And that will be consistent in general under the exogeneity assumption 8 and a standard rank condition. Okay. Now, what would the control function approach entail in this situation? Well, now you have to start making substantive restrictions if you're going to apply a similar method to the one we just did. Notice that equation 9 is now stated as a conditional mean, and we're conditioning on the exogenous variables and the endogenous variable. Okay? But in the end, let's just assume for now that it takes on the same form as it did before. That is, it's a linear function of v2. So understanding this equation is actually critical to understanding the recent cutting-edge work on these kinds of models, because it's saying the following. We know that y2 is correlated with u1, okay? Or at least we think that's true. Of course, we think that the z's are correlated with y2 also. So u1 generally is correlated with everything. Okay? If we just say u1 is correlated with everything, we're not going to be able to get very far. So we have to basically say that it's correlated with these things, but in a specific way. Okay, so this is fairly specific. It doesn't have to be this specific by any stretch, but it can't be completely unrestricted. Okay, so suppose that we say that, well, in fact, it still is depends on this reduced form error in a linear way, V2. Well, now if we work through the conditional expectation given in 10, and now notice this is not a linear projection, this is a conditional expectation, we get the following equation, which looks pretty much like it did before. Both functions of the endogenous variable are still there, and we have this reduced form error. Excuse me. And so the control function approach would be to estimate this equation by least squares after having done a first step estimation to get the V2 hats and plug them in. Okay, now, this is not the same thing as applying instrumental variables on that model 7, where you simply use, say, z2 squared for y2 squared. In fact, even coming up with other possible instruments for y2 squared is not going to produce the same thing as the control function estimates. So now, what are the pros and cons of the difference between the control function approach and the instrumental variables approach? Okay, the control function approach will be much less robust in the sense that there are now substantive restrictions imposed both on the structural errors and the reduced form errors. See, the IV stuff, y2, it wouldn't be, of course, a binary variable if we put a square in it, but it could be some discrete variable with distributions that we don't even care to think about. It could have a pile up at 0, be continuous elsewhere. Anything basically goes as long as you take the equation and estimate it by instrumental variables. The assumption in equation 9, essentially for any kind of models you would write down for U1, let's say for V2, if Y2 were something like a discrete variable, a count variable or something, there's no way that you're going to get equation 9 out of that, okay? Because just to think of a sufficient condition for when you could at least get the first equality there is if the structural and reduced form errors were jointly independent of the exogenous variables. That's a really strong restriction when you write down a linear model for Y2. Okay, it pretty much rules out any kind of discreteness because, you know, once a support of a random variable depends on the exogenous variables, you can't have any kind of independence assumption holding. Okay, independence is not necessary, but something pretty strong is. And so the control function approach, in this particular case, it's less robust in the sense that it imposes significant restrictions on both the structural error and the reduced form error. It's likely to be quite a bit more efficient, too, because what we've done is we've plugged in one function, one control function to handle endogeneity of y2 and y2 squared at the same time. The reason we're able to do that is because we've assumed that this linear reduced form has fairly strong properties. Okay, so how might we go about relaxing that? Well, we could put in, say, v2 squared, for example. We could put in, so those kinds of extensions where we allow the relationship in 9 to be more flexible, it turns out that's pretty much what a lot of the recent literature is about. Okay, it's about more than that in the sense that the reduced forms are going to be allowed to be nonlinear in the z's as well. But a lot of the recent work is basically rests on this notion that you can still get a relationship between the structural errors and the reduced form errors, and the exogenous variables don't show up there separately on their own. Okay, so you can fiddle around with that functional form. Okay, and it's and then so you would put in v hat and v hat squared, v2 hat and v2 hat squared. But the cost, the reason we typically don't do that is because we usually think about What are the weakest assumptions where we're going to get consistent estimates? And the control function approach just applied to this simple extension of that model would be significantly less robust. It really would only, you only have a shot if y2 is continuous, any discreteness, and we're going to probably not have a consistent procedure. So just to show you that how this works when we explicitly recognize that y2 has special features, if instead of just using two-stage least squares or the equivalent control function approach based on linear projections, what happens if we actually recognize that y2 is binary and we want to use a control function approach based on that expectation in 11? Well, this is going to lead to something pretty familiar. The expected value of u1 given z and y2, this can't be written as just a linear function of z and y2 anymore. Okay, so this just shows you probably the leading case once we deviate from a continuous endogenous variable, what's going to happen. But if we make some distributional assumptions, of course, we can compute that expectation, because if we know a joint distribution for u1 and v2, then we know the distribution of u1 conditional on z and v2, and from that we can get the distribution conditional on y2. Actually, I'm jumping ahead a little bit. There's really no v2 left here because I call it e2 down in the next line, which is that y2 follows a binary response model. And so if we assume that u1 and e2 are independent, the easiest thing to do is just to make the joint normality assumption, although, as you can see, I've written down somewhat weaker assumptions there. Then you can derive the expected value of u1 given z and y2 as in equation 12. Often this is written out separately for y2 equals 1 and y2 equals 0. I actually think it's quite informative to have it written out all at once, because it makes you understand that this is a problem of endogeneity of y2. It doesn't have anything to do with sample selection as it does when we have missing data, a topic to be covered later. So equation 12 derives the control function in this case. This is sometimes called a generalized residual in literature on limited dependent variables. So this generalized residual, or function of the inverse Mills ratio, gets added as an additional regressor, and this controls for the endogeneity of y2. Okay. So again, and so of course this leads to the celebrated two-step estimation method, where in the first step you do a probit and then you compute inverse Mills ratios. And again, in this model, you wouldn't do separate regressions for y2 equals 1 and y2 equals 0, because that wouldn't impose the restrictions on the coefficients that they're the same that there's no interaction basically with y2. So you get this method where you add this generalized residual, and that corrects for the endogeneity of y2. So how does this compare with just estimating the original equation by instrumental variables? Again, this is much less robust because it takes the probit model for y2 quite seriously. And not only that, it actually essentially makes the normality assumption on u1, which remember is the structural error term. So u1 couldn't have heteroscedasticity because basically u1 and E2 are both being assumed independent of Z. So the control function method based on deriving this expectation in 11, again, it's going to be more efficient than using instrumental variables. It uses a lot more information. And in fact, you could do the most efficient thing by using a joint maximum likelihood procedure, okay, under joint normality. But it's costly, because if anything about the joint assumptions, the joint normality and independence assumptions fails, then this is no longer going to be consistent. I noticed that Stata does exactly this in what it calls its treatreg command, but the question is, why do it? And the answer is, well, if you want a more efficient but not as robust estimator, you would do it. There are reasons that we'll adjust this model a little bit and talk about where this sort of procedure becomes fairly indispensable if you want to estimate an average treatment effect. Okay, but in this particular case, there is a procedure that's perfectly suitable, and that is to just use two-stage least squares. By the way, just to complete this thought, I often get asked, because when y2 is binary, people are just dying to do something about the fact that it's binary, right? That there's this endogenous right-hand side variable and it's binary, and two-stage least squares just doesn't seem sexy enough or something, that you're just using this linear reduced form for this thing that's y2, and that's a linear probability model, and isn't there something wrong with that? Well, no, of course there's nothing wrong with it, but if you wanted to do something different, then you could act as if the probit model is your best guess at what the right model for y2 is, and estimate a probit and get the fitted values, and then use those as instruments. Not as regressors, right? You don't want to use those as regressors. You want to use them as instruments. So this gives you a way to use the binary nature of y2 if you must. But in the end, all that matters is you're only going to get a very different answer if the probit model predicts y2 very differently from a linear probability model. It often doesn't actually make much of a difference. Okay, but that's just as robust in the sense that as long as you use those as instruments and don't take the probit model seriously, it's fine. And it turns out there's a set of assumptions under which it's the efficient IV estimator, and those two assumptions are given at the top of the slide. Okay, so if the probit model happened to be true and the structural error was homoscedastic, then this turns out to be the efficient instrumental variables estimator. So that is one reason you might want to do it. Okay, so this those examples are in the case where, if you want to think about where the coefficients are homogeneous. So in the treatment effect stuff that Guido talked about yesterday, that's the case where you're assuming constant treatment effects. So I'm taking a less modern approach to this sort of stuff and saying, well, suppose we now write down a model explicitly with a random coefficient on the endogenous variable. Heckman and Wittlasil call this a correlated random coefficient model, which is a useful terminology, because the idea is that A1 is a random coefficient. So this is written in the population where I try to stick to the convention that anything that is Greek is a parameter, and anything that's not Greek is not a parameter. Okay, so A1 is a random variable that interacts with Y2, and then its mean is alpha 1, which would be the average, the population averaged effect. Or if Y2 is binary, it is the average treatment effect. Okay, so what happens in these kinds of models, IV versus control function? Well, this is quite a bit harder to deal with, as it turns out, interestingly enough. You would think this is a modest extension to the basic model, but now anything you do doesn't come for free, because if you really want to estimate the average effect, you have to start making some assumptions. And so one way to see the problem is to write the equation as in 14, where now the model has been written with a constant coefficient on y2, so alpha 1 is the parameter we hope to estimate. But now there's this interaction term where V2, which think of as the unobserved part of the individual specific deviation from the population mean, interacts with the endogenous variable. Okay. Now, if Y2 were exogenous, this would be a minor nuisance, right? This would just induce heteroscedasticity into the equation, and you would ignore it, right? In fact, the whole literature on random coefficient models, once you assume the coefficients are independent of the covariates, you have almost nothing, right? Because it's just a particular kind of heteroscedasticity that's introduced. It becomes much more interesting when that thing interacts with an endogenous variable and the coefficient is allowed to be correlated with the endogenous variable. So if this is an earnings equation where y1 is log of earnings and y2 is, say, schooling, then this model allows, say, unobserved talent or ability it allows the return to schooling to depend on unobservables like talent and ability and so on, and it also allows those things to be correlated. Okay, so that certainly is an attractive setup if you can estimate it. And so the problem with applying standard instrumental variables methods to equation 14 or thinking of it as 15 where you just say, well, leave that interaction in the error term and let's just move ahead, is that this term, V1Y2, down at the very bottom, is in general correlated with any function of the instruments that we can think of. Okay, and so we have a situation where the error term is correlated with the instruments. So the problem is not just that even if we make the assumption in 16, which again is a standard kind of exogeneity assumption, although it is stated in terms of conditional means, this isn't enough for IV to be able to consistently estimate that average effect. A sufficient condition, though, is that the covariance between V1 and Y2, so you can think of this in terms of actually the reduced form error for Y2 also if you want, although that you don't actually need to write down any kind of particular functional form to think of this condition. A condition that is sufficient is that even though V1 and Y2 might be arbitrarily correlated, so this does allow for correlation between the slope and the endogenous variable, it rules out the case where the covariance is a function of z. Okay. Now, so this is an assumption that can hold under joint normality, although as it turns out, certainly just saying that, yeah, this is a sensible condition for cases where y2 is continuous is much too strong. In fact, David Card showed examples where this condition clearly is not true in exactly the example that I pointed out, the schooling equation, the earnings equation with schooling endogenous. So this assumption is hardly for free, even if you're thinking of the case where y2 is roughly continuous, we'll call it. That nothing is ever really continuous, so the question is it continuous enough? And certainly 17 fails in the case where y2 is discrete. That is, if you think of y2 being a binary variable that follows a probit, 17 simply is not true. Okay, so, but it does give us something, and it actually gives us something to compare with control function methods and other kinds of methods. So in the notes, this control function approach that was suggested by Guerin in 1984 under joint normality for everything. So in other words, the structural error U1, the random coefficient A1, and the reduced form error V2, if those are jointly normal, then you can derive a control function approach for this problem. Actually, you can relax those conditions a little bit, of course, as always, but not a lot that makes a big practical difference, I think. And the control function approach in that case is simply to add not just the reduced form residuals, but the reduced form residuals interacted with y2 itself to the equation. Okay, and that you can show under those assumptions that does produce a consistent estimate of the average treatment effect. Okay, but again, the key assumptions there are essentially putting a restriction, a very strong restriction on the reduced form of y2, conditional normality with a linear mean and homoscedasticity. Okay, so that turns out to be, those assumptions are quite a bit stronger than in equation 17, which, while ruling out discreteness in y2, certainly does not require y2 to be normally distributed. Okay, and it doesn't require anything. Notice that the structural error U1 doesn't show up in that condition either. So that's pretty much unspecified except for 16. So basically, the argument so far is that the standard instrumental variables estimator looks pretty good, at least in terms of robustness. Now, whenever you do these things, of course, you want to compare precision, and as I said, the control function method assumes more, so you should get something for that. But if you apply Guerin's method, as at the bottom of page 9, then, of course, you have to adjust the standard errors to make that comparison fair. Okay, now, so let's continue with this a little bit. I will get to stuff that's newer, but I do think it's useful to see how all of these things fit into basically one framework, and then the issue is, are you able to use an IV method, or do you really have to go to something like a control function method that imposes more assumptions? And in the cases where there's no heterogeneity in the treatment effect, I mean, this is basically a conclusion from Hito's work, and then you don't have to worry about it, right? You just use standard IV methods and move on. But if you are worried about heterogeneity, then the nature of Y2 suddenly plays a big role. And so if we now change the model, we don't change the model, we still start with 13, but now Y1 is a binary treatment. Okay, so this is a case explicitly with a binary endogenous variable, but where the treatment effect varies by individual. Now what are we going to do with this? Well, 17 can't be true. Okay, and we know what the IV estimator estimates in general. It estimates the local average treatment effect. Okay, might we be so heroic to think we could estimate the average treatment effect? Well, this is the old-fashioned way of going about this. The answer is yes, if we make enough assumptions so that we can derive this control function method, and that's given by this unnumbered equation, which I left unnumbered, I think, because it made it go off the end of the page, although I see didn't have to do that. So this is an equation that you often see in the context of so-called switching regression models. And this H2 is, again, this so-called generalized residual function. And now what happens is the control function approach leaves Y2 in. It includes this generalized residual, which is a function of the Mills ratio, just as before. But now you also have to interact that with Y2 itself. Okay? And now this produces consistent estimates of the coefficient alpha 1 on Y2. And so, of course, the two-step method is to do a probit, and then again, this is not, the switching regression does this in two steps where the implicit assumption is that Y2 interacts with the exogenous variables as well. And you can do that by, of course, just adding Z1 interacted with Y2 to this equation. So this, I think, is actually the cleanest way of stating what's going on. It's no different from computing E of Y1 given Z of Y2 when Y2 is continuous in principle. It just looks different because we have to make sensible assumptions about the distribution of Y2. So one thing that I haven't actually seen in this, using this approach is when you take this as a control function method where it's being used to solve the problem of endogenous random coefficients that are correlated with the endogenous variables, then you might want to allow the coefficients on the exogenous variables to be random as well. The switching regression framework doesn't seem to allow for that, but interestingly, it's not the case where you just say, well, that's on an exogenous variable. I can just leave that in the error term. You can't do that anymore because you're conditioning on y2 in this expectation. And so the most flexible thing to do, I guess I didn't write it out, but oh, there it is at the bottom, is to interact this generalized residual with everything, because that would allow the coefficients on Z1 to be random as well, although there's a joint normality assumption underlying that for the random coefficients. But anyway, if you're going to allow heterogeneity on Y2, why not on the Z1s as well? Okay, so that's all for models that are linear in the parameters, and with that background, we can now turn to models that are where the structural model is not a linear model. And unfortunately, we don't really have simple things like linear instrumental variables to apply in these cases. Actually, I'll take that back. We do have those things. We can just say, suppose y1, the response variable, is binary, then we can just estimate a linear probability model treating y2 as an exogenous variable. Josh Angress certainly has pushed this view that functional forms, when you're interested in average effects, they don't seem to matter much anyway, and so why not? But again, presumably not everybody is taking that view, so the question is, what else can be done? And you'll see in some ways, I think Josh's view on this is basically frustration, because there's actually very little that we know. I mean, that econometricians, in a sense, are nibbling on the edges of this problem, because once you allow general discreteness in y1 and general discreteness in y2, we don't really have good answers, basically. You can always say, model them jointly and do maximum likelihood, right? That's always an answer, but it's not perhaps what we're looking for. So in this particular case, let's just look at a binary response problem first. And unlike in a linear model, where the nature of y2 wouldn't matter, the nature of y2 matters a lot. It determines basically what we're going to do in terms of whether we can actually come up with a sensible control function procedure or some sort of two-stage least squares analog of a linear model. So Blundell and Smith and Rivers and Wang looked at this model where y2 is a continuous variable, and in fact it's more than continuous. There have to be some restrictions put on it, and again, this is a little stronger than necessary, but the way to think about the kinds of restrictions that are needed are that the reduced form of y2 is this, well, it's a classical linear model, and then jointly the u1 and the v2s are independent of z, and then bivariate normal, in fact. Then when you work out what the control function is in this case, which again, so equation 22, this is exactly the sort of thing we derived before. Because y1 is binary, this is the expected value of y1 given all the exogenous variables and y2. And it does have a probit form, but it has a probit form because of all the normality that's floating around in this. So, and notice also, of course, when you derive this equation 22, the coefficients all get scaled by a conditional variance, okay, which is 1 minus rho 1 squared, which is the correlation between u1 and v2. Okay, and so the two-step method in this case, the control function approach, is to get the residuals from this linear reduced form and then do a probit where you add these residuals, and again, this controls for the endogeneity of y2. The nice feature of this procedure is that, like in the linear case, this gives you a simple test for endogeneity. And in fact, the test is valid quite generally. You don't need to assume, because under the null y2 is exogenous, and so it doesn't really matter whether it has a normal distribution or anything like that. This can be treated as, this is just a simple specification test. So once you've done that, it turns out you certainly have enough information to recover the so-called, the structural parameters that show up in equation 18, which means that you can compute the averaged partial effects where U1 gets averaged out because it's not observed. But for reference later, it's also possible to compute the averaged effects by an equation like 23, which, so x1, it just contains z1 and y2. And so the so-called average structural function, which we're going to then take changes in derivatives with respect to the elements of z1 and y2, can be estimated as an equation 23, where notice what's happening is we're averaging out those reduced form residuals. And notice those are the scaled coefficients that are in that expression. We don't go back to the original coefficients and then compute this. We actually use the scaled coefficients that are obtained from the second stage control function estimation. The one thing that's useful about this approach, I don't know how many of you deal with so-called fractional response variables, but the same sort of method works if you start with an omitted variables formulation as in 24, where y1 could be anything that sensibly has a mean that's bounded between 0 and 1, that is some sort of fractional response. And then if you go through the same kinds of manipulations, you get exactly you get a control function that looks exactly like the one we already derived. The difference is that y1 no longer has a known distribution, and so you're not doing a second stage maximum likelihood, you're doing a second stage, what's usually called quasi-maximum likelihood, which is perfectly fine because the Bernoulli log likelihood has this nice property that as long as you have the mean correctly specified, you get consistent estimates even though the distribution is completely wrong. So you can do that, or of course you could do nonlinear least squares, which is always consistent for conditional means. So again, the point is that you can do all of this where y1 is just any variable that's between 0 and 1. It could have a pileup at 1 or 0 or both or somewhere in between. Well, if you believe model 24 basically and you're willing to make these kinds of normality assumptions, the same thing goes through. And you can estimate the partial effects based on equation 23 as well. Okay, and then in a paper that I did, you can make this more robust, more flexible. You can model variances and so on to allow heteroscedasticity, but I'll let you look at the notes for those sorts of extensions. Now, this control function approach in this particular setup can be compared with another approach that is commonly used, and that is, this is the attempt to mimic two-stage least squares. That is, in the first stage, you regress y2 on the z's, just as you do for the control function approach. The difference is whether you get the fitted values y2 hat or the residuals v2 hat. In the quote, two-stage least squares approach, you take y2 and, of course, you replace it with y2 hat. That's the analog. It's hard to figure out when that would be preferred to the control function approach for a couple of different reasons. First of all, it doesn't deliver a simple test of endogeneity for y2. Okay, that's probably the most important reason. Secondly, the parameters that you get are a real mishmash of the things that you wanted to begin with. And there's no simple formula like equation 23 to get the average partial effects. Okay, so so the question is, do you get consistent estimates of the parameters after you undo everything? The answer is yes, but you can see that those, actually, I didn't write down what this, if you look a few lines down, there's this parameter omega 1, and it's the scale factor that shows up in doing this procedure. You know, it's a complicated function of, it's a function of variances and covariances, and so you have to figure that out. Certainly it's doable, but it does give you different scaled coefficients too. So you do want to be careful if you do the, quote, two-stage least squares approach and you do the control function approach, these coefficient estimates have different scales, so you shouldn't try to compare them and say, gee, one of these is wrong. They're just scaled by different things. And my argument is that the scale that the control function method uses is more useful because of equation 23. Okay. Plus, I know no one in this crowd would ever do this, but this avoids the temptation of when you add y2 squared to the model that you're not going to plug in y2 hat and square it, right? And in the control function approach, you can't tempt yourself to do that because adding the v2 hat controls for endogeneity no matter how y2 shows up. Okay, that's another advantage of it, is that I didn't emphasize this, but if you really believe y2 has this linear reduced form with an additive normal error, then y2 can show up in any way in the structural equation. That is, any way interacted with, say, the exogenous variables or quadratic and so on. It can't have a random coefficient, but it can be a fairly complicated nonlinear function. So I think that's a clear advantage for the control function approach in this case. So you can see if you just simply added the extension that you wanted y2 to show up as a quadratic or want it to interact with the exogenous variables, very sensible things, then the control function approach, while maintaining a lot of assumptions, is easy, and it doesn't maintain anything more than the, quote, two-stage least squares approach, which is wrong. Okay, it's not just a matter of is it less convenient. It's just wrong in those extensions. Okay, so I don't want to talk about this too much, but to show you that, again, the somewhat sad state of affairs in some ways about what else we can do is that if you take this equation and you add a random coefficient to y2, well, you can work this all through again with y2 as normally distributed and so on. But when we go to talk about extensions to cases where we say non-parametrically we don't specify, say, the function phi in any particular way, those sorts of extensions are actually, I take that back. We can handle things like that up to a point as long as y2 is not discrete. I'm jumping ahead a little bit. Okay, when y2 is continuous, we can actually do a lot. Okay, but let's see. Okay, so there is some work recently that allows us to estimate coefficients up to scale in this binary response model where we just, of course, write y1 as this indicator function, and then the goal is to estimate the coefficients delta 1 and alpha 1 up to some common scale. So this is a case where the interest is clearly not in the magnitude of an effect, but in the direction of the effect and how what its size is compared with other explanatory variables. And this is actually a hard problem in general. And Lubell's approach, it assumes a fairly strong assumption, and the assumption is that there's a special regressor in this model. And that's the special regressor. That's not my terminology. That's actually his. The special regressor, the easiest way to think about it is it has to appear in the model, and in fact, its coefficient is normalized to 1, and it basically has to be independent of everything else. Okay, so it has to be independent not just of the exogenous variables, but also of the endogenous variable. And you can think of some cases where that's true, but you can't think of, I think, many cases where that's true. So even if you're just interested in the coefficients, it's a little hard to see how that would be generally applicable. Okay, so let's return to this case where we actually have a parametric model and start talking about where things stand in terms of relaxing distributional assumptions. Basically, if y2 is a discrete variable, very little is known, and even the semi-parametric, non-parametric stuff I'm going to mention really excludes that case. So if we start even with a model which is parametric, like at the top of that slide, and then we say y2 is hidden in x1 somewhere. In fact, it could even be the standard additive structure, but y2 is just some discrete variable. Basically, we've failed in providing good estimators for that case. There are, of course, some poor strategies that one might hope work but don't. You can try plugging in fitted values from a first stage estimation. So in the binary response case, you might model y2 as a probit and then try to stick it inside a second stage probit, and we know that does not work. Although as recently as 3 weeks ago, somebody contacted me wanting me to tell them that yes, that did work. It doesn't. So that basically the strategies we have are to do a joint maximum likelihood, because the control functions, see, the problem is there's no simple way to derive a control function except by having a joint distribution. Okay, so if you have the joint distribution, then you might as well do maximum likelihood. So what you would like, of course, is to be able to derive a control function approach that doesn't rely on distributions for the reduced form. But we really don't have those methods available yet. By the way, as a practical comment, I think this is pretty widely known now, but again, this has come up fairly recently. When if you have y1 and y2 that are both binary, and you're in the situation where it's an omitted variable context and y1 is assumed to be a function of y2, and you think y2 is correlated with some omitted factor, and so y2, you're willing to specify that reduced form of y2 follows a probit. The question is, can you apply so-called bivariate probit to this case to estimate everything, even though the bivariate probit model is typically written with exogenous explanatory variables? And the answer is yes, you can, because of the way the likelihood function factors. So you can actually include y2 in a completely general way in the structural model, as long as its reduced form follows a probit, and use the so-called bivariate probit approach to estimation. Okay, so one of the key features of the Rivers-Vuong approach, control function approach for the probit model, is it has normality floating around all over it. Okay, so, or at least there's normality somewhere. And this becomes a problem to apply to multinomial responses, because multinomial probit is computationally hard.